Moving on to the next topic in enzymes, we move forward to enzymes nomenclature and classification. The first question that arises is that why does there was a need for the classification of enzymes? See, initially when the discovery of enzymes started to begin and one after other enzymes were discovered, their names were given which now if we see they are vague in nature. I mean, they have been named after the substrate, the origin place in the language. If it can be in German, French, anything that is not compatible with the whole world, the whole earth. Scientists need to have a common nomenclature system for particular things. Nomenclature of enzymes has undergone many changes over the years. The name assigned to enzymes in the beginning were very vague and uninformative. Some of these earliest names, including pepsin, tylin, zymase, indicate neither the substrate of the enzyme nor the type of reaction that they catalyze. Later on, a slightly more informative nomenclature was adopted. A suffix ase was added to the name of the substrate like lipase, protease, ribonuclease. Still, this type of reaction, the type of reaction that the enzyme is catalyzing is not was not clear. The nomenclature was modified further to include the name of the substrate followed by the type of reaction ending with ase. So this resulted in the names like lactate dehydrogenase, pyruvate carboxylase, glutamate decarboxylase, etc. Even these names do not give complete information about the reaction. For example, whether a coenzyme is required or a byproduct is formed. To make the names of enzyme precise, full, informative, and unambiguous, International Union of Biochemistry devised a method of nomenclature and classification of enzymes. According to International Union of Biochemistry, the enzymes have been divided into 6 classes, numbered from 1 to 6. Each class is divided into a further subclass, and each subclass is divided into subclass, and each subclass are divided into individual enzymes. The name of the enzyme has two parts. The first part includes the name of the substrate, including coenzyme if they act as a second substrate. The second part includes the type of reaction ending with ase. If any additional information is given, it is put in parentheses at the end. For example, the enzyme having a trivial name glutamate dehydrogenase catalyzes the following reaction. L-glutamate plus NADP plus water leads to the formation of alpha ketoglutarate, NADPH plus proton plus ammonia. According to IUB system, this enzyme is known as L-glutamate NADP oxidoreductase deaminating. This name shows that the enzyme acts upon L-glutamate, NADP, and NADP is required. The type of reaction is oxidoreduction, that is L-glutamate is oxidized and co-substrate is reduced. The amino group of L-glutamate is released as ammonia. Thus, the name given complete information about the reaction catalyzed by the enzyme. Moreover, each enzyme has been given a code number consisting of 4 digits, which successively denotes the number of classes, subclasses, subclasses, and individual enzyme. The code number given to L-glutamate NADH oxidoreductase deaminating is EC number 1.4.1.3, which shows that it is the third enzyme of subclass 1 of subclass 4 of class 1. EC is the acronym for enzyme commission. These 6 are the classes in which the enzymes are distributed. Oxidoreductases is the first class, transferases, hydrolases, lyases, isomerases, ligases. If you see individually each class, oxidoreductase, as the name itself suggests, these are enzymes that catalyze oxidation reduction reaction. One substrate is oxidized and the other is reduced. There are several subclasses of oxidoreductases, each acting upon a particular chemical group. The groups undergoing oxidation reduction include these. Examples of oxidoreductases are glutamate dehydrogenases, lactate dehydrogenases, malate dehydrogenases, glycerol 3-phosphate dehydrogenase. All the enzymes which has a suffix of dehydrogenase are known as oxidoreductases. The next class is of transferases. They transfer a group other than hydrogen from one substrate to another. These group may be methyl group, amino group, phosphate हो सकते हैं या acyl group. Examples include hexokinase, glucokinase, fructokinase, glutamate oxalate transaminase, ornithine carbonyl phosphate, etc. Basically, these are enzymes of glycolysis and urea cycle. As the name itself suggests, the third class is hydrolases. So they are hydrolytic enzymes which hydrolyzes bonds such as peptide, ester, glycosidic bonds. They are very commonly found in the digestive tract. We have discussed in early classes also in the digestive tract. The molecule, the macromolecule is breaking down into smaller molecule, which is known as digestion basically, which are easily for absorption. These enzymes are commonly found in the digestive secretion. They are known as, for example, amylases, salivary amylases is an example, lipases, pepsin, ribonucleases, sucrases, lactases, maltases, etc. The fourth class is lyase. They basically they remove chemical groups from substrate by mechanisms other than hydrolysis. They also break the bond, but other than hydrolysis. The groups removed may be water, amino acids, amino groups, carboxyl groups, etc. इनके एग्जाम्पल हैं aldolases, enolases, fumarases, etc. The fifth class is of isomerases. These enzymes catalyze interconversion of isomers of a compound. Examples include alanine racemase, triose, phosphate isomerases, etc. The last class is of ligases. They ligate or bind two compounds together. Since the binding occurs by a covalent bond, a source of energy is required, usually a high energy phosphate. Examples are glutamate synthetase, squalene synthase, acetyl CoA carboxylase, etc. Moving on to the next topic, which is the mechanism of enzyme action. If we see the premises of mechanism of enzyme action, enzyme act by forming a complex with the substrate known as enzyme substrate complex. And by doing so, they lower the activation energy required for the reaction to occur and thus catalyzing the reaction. At temperatures above absolute zero, molecules are in constant motion because of their kinetic energy. Chemical reaction occurs when molecules of reactant collide with each other in the correct orientation. This is known as kinetic theory of reaction. The greater the frequency of collision between reactant molecules, greater will be the rate of reaction. The frequency of collision can be increased by raising the kinetic energy of the reactant molecule. That is by raising the temperature. This would increase molecular motion and hence frequency of collision. The energy level of the reactant has to be raised to a critical level for the reaction to occur. The energy input requires to reach this critical level is known as energy of activation. However, the option of raising the temperature is not available in living organism. Enzymes provide an alternate pathway for this reaction. You can see here the reactant, they lower the energy of activation. You can see here the free energy and progression graph. Here a reactant, if without enzyme, seen in the black lining, it requires more activation energy compared to the red one, which is with enzyme, activation energy is lower. We can understand by this simple diagram here. If a person has to put one rock here, and then the ultimate result would be the breaking of that rock into smaller units. It, he had to make it climb up to the top of this hill, right? He will be requiring a lot of energy. See, a particular set of energy which needs to be used to take this rock up to this level. If enzyme are present in this reaction, then you can see only he has to take it up to here, which is again less amount of energy is required. Thus here you can see the change in the activation energy is there, which is lowering of the activation energy. And the reaction is occurring with low energy compared to normal reaction. And the result is same.